Okay, we're going to take our knowledge of calculus into section 4.5, where we become serious curve sketchers. We are going to go after all the information that we know from pre-calculus and calculus in order to get the curve of a function down as best we can. Really understand it as we go. Now, this is a process. It's a big process, and I explained on the class meeting, there's a recording of the Zoom meeting. There's a lot of work involved, and what I'm going to do is I'm going to show you 3 different examples of the curve sketching process, 1 video each, and here's the first one is going to be this polynomial. But watch what we look for. When you're going through this, you're going to use the knowledge we know from pre-calculus, which takes us to here, wherein we look for domain, we look for maybe intercepts, we look for possibly symmetry, and definitely asymptotes. But we're not done there, plus any other kind of knowledge we have about the curve itself. Then we take our calculus, and find derivatives to find increase, decrease, local max, min, concavity, and inflection points. And when we're done, finally, we can sketch the curve with a greater knowledge of what it's doing. So let's get going. Polynomials are not horrible. And in fact, what I'll do right now is challenge you and say, what do you know or recall from pre-calculus? What can you tell about this guy? Well, first of all, like I said, it is a polynomial. And as a polynomial, it has that kind of spaghetti looking kind of thing that it does, right? What else can you say about this curve? Well, no, polynomial could do whatever. The other thing I see is that it's a 3rd degree. Now, if you remember this, that's fine. If not, okay. But a 3rd degree from pre-calc, it goes up, it bends a couple times, or it can come down and bend, and that kind of weirdness. So knowing that is also useful. It's easy to find a y-intercept. All you have to do is plug in 0, and in this case you get a 2. That's nice. Why don't we do that? And then sometimes they talked about, I don't know if you remember, end behavior. This is all from pre-calculus. That is to say, think of yourself as making x go to infinity, make it go to negative infinity, and what do you think this function does? Well, at negative infinity, you have 3 negatives, but it's being subtracted right there. So really, if you are into end behavior, you know it's going to positive infinity this way, and then negative infinity that way. So that kind of helps you see that maybe the curve is this one. All that knowledge is helpful. You know what? We might have forgotten just about all of it, but hopefully you can find the y-intercept. That's not a problem. So the next thing is, let's start looking at the derivatives. So we have, let me erase this stuff. That's our curve. So the first thing we'll do, the new thing is to take f prime. So f prime is going to be, looks like it's 6x minus 3x squared. We want to, as we've been doing in the past in this chapter, we want to find the critical points and local max min. So the first thing is set it equal to 0 and solve for x. If we do that, maybe we factor out a 3x here. Left behind is a 2 minus, looks like it's an x, and that's equal to 0. So the critical numbers are x is equal to 0 and 2. What do we do with that information? Well, the first derivative, man, we're going to check this guy's sign. We're going to plot 0, we're going to plot 2, we're going to bring out another color, and we're going to test the sign of f prime. Now remember, f prime is this guy. I'll write it again. He's 3x and 2 minus x. We found where it's 0, but now we're going to try the other regions and see where it's positive and negative. So maybe you plug in x is like, I don't know, -1. Here you get a negative. And then 2 minus a -1 is that's positive, okay? So the whole thing is negative when you go negative times a positive. So the function itself is what? Decreasing. Let's do 2 more times so we get it. X is equal to maybe 1 from this region. Well, 1 is positive there, but you put a 1 here, 2 minus 1 is positive again, so the whole thing is positive, and I guess the function's increasing. One more region, how about x is equal to maybe 3? Well, in that case, it's positive again, but look at this. 2 minus 3 is negative, so the whole thing is negative, and it's decreasing, and it's more ammunition for that shape of a curve, isn't it? Well, we found intervals of increase, decrease, and sometimes the test would say, tell us what those are. So you could say f is increasing on, right? and you name these intervals. It's increased, well, only one, from 0 to 2. And f is decreasing on, let's see, two of them, minus infinity to 0, and also 2 to infinity and beyond, right? And we also have the following information. I'll put this in another color, maybe green or something. And that information is that since it goes down and up again, this is a min. Up and down again, this is a max. So we're going to tell the world that story too. We'll say, oops. We'll say, okay, it's doing something funny. What do we say as I try to fix this thing? There we go. What we'll say is f has a minimum of, and then you write f of 0. We already know that answer. It's 2. And then f has a max of, and you plug in f of, in this case, 2. And that turns out to be, if you do the numbers, what do you get? Looks like you're going to get a 6, isn't it? I'm plugging in, that's the thing that's important to you guys to understand. I'm plugging into the original function. So plugging in a 2, 12 minus 8, oh well, 12 minus 8, no, that is 14 minus 8 is 6. Okay, so we're getting a 6 here. Okay, it's time to go on to the second derivative, but before you do, you know what you do? You get impatient. I can graph this thing. All right, go ahead, go ahead. So take out your paper, because this is where the, what is it, the rubber meets the road, and mark off what you've got. What we have is information that says, first of all, there's a min of x 0, 2 right there. And then if you march over to 2 and go up to 6, this is the point 2, 6, that's a max. Okay, do you see what's happening with the curve? That with the information that you're decreasing to the left here and increasing and then decreasing, you can kind of gauge in a kind of crooked hand what the curve is looking like that. Okay? Well, we're not done, because what we tend to do next is we look at the second derivative, and I look at the first and I go derive that, and I get 6 minus 6x is 0, because I want to see where the sign changes. Well, obviously, if x is 1, that's, well, it's a possible inflection point this time. So now we're testing the sign of f double prime, which is 6 minus 6x, and we're going to go on either side of 1 and choose a color. And maybe I choose, how about x is 0? If x is 0, I get positive. Guess what? That is concave up. If x is 2, plug it in right there, you get negative. It is concave down. So what that means is that f is concave up on, and then you tell the world it goes from minus infinity up to 1, and f is concave down on, and that one is from 1 to infinity. But not only that, take a look at this chart here, this sign chart. The concavity changed on either side of 1. So because it went from plus to minus, this is an inflection point. So that's the last thing we would say. We go, f has an inflection point, and it is, let's see, you plug into the function the number 1, and out would pop a 4, okay? So at 1, 4, let's pretend that's it, it's an inflection point. So what does that mean graphically? It means that the curve, you see the concavity to the left of 1 is up, and then the concavity is bending down. And that's all she wrote about this particular polynomial. If you were in pre-calculus and they said find the x-intercepts, how many are there in this picture? Only 1. So if you remember pre-calc, you'd get one rational root, and then you get 2 complex conjugate roots. Remember that jive? Well, that's what's going on here. And that's it for polynomials. The rest are even crazier. But thanks for listening.